So we're going to finish out our unit on rotation with our notes today over angular momentum. Okay, so that is the topic of our notes. We're going to calculate angular momentum, moment of inertia, and angular velocity, and discuss the relationship between these variables and determine whether angular momentum and or energy is conserved for given scenarios involving rotational collisions. So today's notes, we'll see how quickly we get through them, but as I said, are the last set of notes, so it's kind of trying to, we'll add something new, but then pull some of the other stuff back in. As a reminder, playlist 4 is due tomorrow, so the notes today should help you with some of those questions if you got stuck on any of them involving angular momentum. That's in today's notes, and then you have a test on Monday of next week. That is your multiple choice test. Your free response test is on Wednesday of next week, and as I said, tomorrow is a work day and Friday is a review day for you to get prepared for those upcoming tests. So let's go ahead and get right into it with a reminder, because we have talked about momentum before. We've talked about momentum when we discussed linear momentum in our previous unit when we were talking about translational motion. So as a reminder, momentum, when we talked about it previously, we defined it as mass in motion. But we were talking about it as translational motion. You can also think of it as detection of an object's motion, the quantity or measure of the object's motion. There's different ways to define it. But when we talked about it with translational motion, we used the equation P equals m times v, where that P was momentum and the m is mass and that v was your linear velocity. Today we're going to bring in objects that are in rotational motion, and so we're going to talk about angular momentum. And angular momentum, of course, is going to be the detection or the measure of the object's rotational motion. Okay, and so it's going to be similar in terms of how we calculate it, and we'll look at that in just a minute. But we've seen that same pattern throughout, where our equations that we're using in rotation are kind of similar to our equations that we used previously with translational motion, and the same thing is going to hold true here. Okay, because just like momentum, our linear momentum was mass times velocity, our angular momentum, L, is moment of inertia times angular velocity. And those are the same variables, but for rotation that we've been using. So again, before you can actually use this equation and calculate angular momentum, which is represented by a capital L in the equation, it is necessary for you to first define the axis of rotation. So you have to take a look at what is this object rotating about? Where is that axis? So that you can then analyze the values for that equation. But again, this is your formula. L equals I times omega. Your units that you're going to get are, of course, going to be your units for your moment of inertia multiplied by the units that you have for that angular velocity. And you're going to end up with kilograms meters squared per second. Just as a little side note, the units that we got when we calculated linear momentum in our previous unit were kilograms meters per second. So the units are not the same. They are similar, but they are not the same thing, because this is kilograms meters squared per second. So just a heads up, the unit is different because the equation is different. Okay, but again, that is your angular momentum formula. And in our previous equations, we used I, that moment of inertia as mass is kind of the rotational equivalent because it's your mass distribution, and angular velocity is that rotational equivalent to translational velocity. So the equation does look like the other that we used previously. So when we talk about angular momentum, you do need to know that it is a vector quantity. So was linear momentum. This is too. That points along the axis of rotation, and that's why it's so important that you identify where the axis of rotation is, because that is actually the direction of your angular momentum will be along that axis of rotation. And so the value is going to depend upon that. To identify the direction, okay, to identify the direction of your angular momentum, we use the right-hand rule. If you took honors physics previously, you've heard of a different right hand rule, but it is effectively done in the same way. So this will not be as new to some of you. But in order to do this, you're going to take, first of all, your right hand. It is called the right hand rule, so you do have to use your right hand. But if you take your right hand and you curl your fingers like this, so it looks kind of like I'm giving a thumbs up, you're going to be curling those fingers in the direction of the rotational motion. So depending on the picture that you're looking at, okay, you might be curling your fingers or turning your hand accordingly. But your thumb will point in the direction of the angular momentum vector. Okay, so let's take a look at an example. This one says a disk rotates clockwise about its center of mass. Find the direction of its angular momentum. So again, you're going to take your right hand and you're going to curl your fingers in the direction of the arrow that you see there. Pretend that you're reaching into my screen and behind it. And if you do that, you can see it's not going to be this way. I have to rotate my hand this way so that my fingers can come out from behind and wrap around. So you have to kind of rotate your arm so that it looks like this. Okay, so that your hand looks like this. Your fingers wrap around, pointing in the direction of that rotational motion. You can see it right here. Imagine your fingers wrapping around the front of this rod. You can picture it here, and then your thumb will point in the direction of the angular momentum vector. So in this case, L, your angular momentum vector, would be drawn downward. Due to the direct relationship between L and omega, these will have the same direction. So when we're looking at the direction for both, you can get it this way. So that's how you would draw the vector. Okay, so that is your angular momentum. And again, right hand rule. It's probably going to take some practice for you to get used to it, but make sure you use your right hand. Obviously, if you use your left hand, you will have the exact wrong answer. Okay, so of course, if you have just one object in the system, then there's only one thing to consider. But if you have multiple angular momenta in a system, then you can add up the vectors to get the total. We've done this before as well. But if you want to get that net angular momentum, it would be the sum of your angular momenta, and it would be the total of those that were in the positive direction plus the total of the angular momenta in the negative direction. And of course, in their opposite directions, we're technically subtracting here, not adding, if you do have momenta in both directions. And so it's the same process we've used anytime we have found net anything. Same thing. So get the sum of the positive direction and then add to it with the sum of the negative direction, keeping in mind that that direction, is usually denoted by a sign. So you'll have to define what positive and negative are. So again, if you have multiple angular momenta like you would have in this teacup ride, because there's a lot of different things spinning in a lot of different directions, then you could add them up to get the total. All right, so when we talk about momentum, and when we spoke about it previously, we talked about conservation of linear momentum. We are also going to discuss conservation of angular momentum. And it's going to sound kind of similar because with our linear momentum, when we had no external net force on a system, then we had conservation. If we had no external forces acting on it, it's similar here. If there's no external net torque on a system, then the angular momentum of the system is constant, meaning that the initial angular momentum L naught will equal the final angular momentum L for that system. Of course, you need to be careful when you're defining your system and when you're defining your axis of rotation so that you're able to make sure that that net torque equals 0 so that you can use this law of conservation of angular momentum, because of course you cannot use that if you have a net torque. So we're going to need to be careful with the way that we define our systems. If we're trying to solve something using this equation, we need to define our system in such a way that the forces are internal to the system and therefore not something that's going to cause a change in the angular momentum of the system. Okay, so that's this note down here. If you're trying to use this, make sure that you define your system so that you have 0 net torque on your system. All right, so let's look at just an example of how we could define a system and maybe start to analyze it. So here I have an example of a figure skater spinning. Again, I want to analyze this scenario in terms of conservation of angular momentum, so I need to define my system so that my net torque is 0. And if I want to do that, I'm just going to call the system my skater. Okay, my axis of rotation that the skater is rotating about is going to be through the skater's center of mass to the contact point between her skate and the ice, and it would look something like that. Okay, I put her center of mass kind of roughly in the center of her body, but it's wherever her center of mass is. So forces that are present on the skater. Let's see if we have a net torque. I know that the skater would have Fg, a force acting downward from her center of mass. I know that we would have Fn, a force acting upward from the contact point between her skate and the ice. Do either of these produce a torque? We talked about torque previously. Would either of those forces produce a torque? No. Yeah, Grayson's shaking his head. And that's because they're along the axis of rotation. Remember, if you want that force to cause a torque, that force has to be applied perpendicular to the axis of rotation. Therefore, neither of these causes a torque, and thus our net torque is 0. Our net force is also 0 because they would technically also be equal and opposite to each other. But either way, we do not have a torque here at all because neither of these forces would produce a torque on our skater, which means we have no net external torque, which means we can analyze the system in terms of conservation of angular momentum. Okay, now if the skater were to do something like this and extend her leg is of course part of her, and that is therefore part of the overall system, and so that would be an internal force to the system, and it is something that skaters do. But those internal torques within the system do not change the system's angular momentum. And so if you were to skate doing this, or maybe you spin in your chair and you put your legs out and then pull them in, if you've ever tried that, I don't know. I'm not suggesting that you do it right now. But either way, because that's an internal force on yourself and it's part of the system, you're going to have conservation of angular momentum. Thus, the angular momentum of the skater on the left here is equal to the angular momentum of the skater on the right. However, that doesn't mean that her speeds are the same, because they're not. Okay, if you look at these two scenarios, in this position, her moment of inertia is different than it is here. Her mass distribution is different. Okay, when she puts her arms out, she has a different distribution of mass and a higher moment of inertia than she does whenever she brings everything in. Okay, and so changing that moment of inertia is going to cause an inversely proportional change to the angular momentum of the skater, because again, in order for the angular velocity, because the angular momentum has to stay constant. So whenever she extends outward, she's going to have a smaller angular velocity. She's going to move slower. Whenever she pulls everything in, she's going to spin faster. And again, if you've tried this before, whether you were on skates or just spinning in your chair, you probably already know this. Okay, but you can slow down by putting your limbs outward to have a greater distribution of your mass outward. And you can see it here. Here's a skater doing it. So her arms are out. She's going to bring them in, and when she does, you can watch her get faster. Because she would, as she brings her mass inward, she's going to increase in her speed. All right. So again, there's no net external torque here. Everything that's happening is within the system. So she has the same angular momentum, but she does not have the same velocity. All right, so again, back to the same example. What is happening to her kinetic energy whenever she does this? Okay, again, as a reminder, kinetic energy, when we're looking at rotational kinetic energy, because that's all we have here, she's spinning in place. The equation for rotational kinetic energy is 1/2 I omega squared. Omega squared would, of course, be omega times omega. And if we write it out like that, I times omega is the equation that we just learned today. That is your equation for your angular momentum. So you could rewrite the equation like this. that her rotational kinetic energy is equal to 1/2 times her angular momentum times her angular velocity. And so if we look at the equation in terms of these variables, we know that her angular momentum stays the same because all of those forces are within the system. Okay, but we know that she has an increase in her angular velocity when she pulls her arms in. And so her kinetic energy, her rotational kinetic energy obviously increases as well because her velocity is increasing, but her angular momentum is staying the same. Okay, now we've talked about this before. In order for us to have a change in energy, there has to be work being done somewhere. So her kinetic energy is increasing, but how? Where is that work occurring? Does anybody know? It's okay if you don't. We haven't talked about it yet. I'm just curious if anybody had a guess. She does work when she pulls her arms inward. Again, it's all internal to the system. Okay, but that's where her increase in velocity is coming from. When she pulls her arms inward, she is doing work as she brings them closer to her body. Okay, so that's where our increase in rotational kinetic energy is coming from. And again, we have the same angular momentum, but we have a change in our angular velocity whenever she does that, because her moment of inertia has changed. All right, so let's talk about rotational collisions. So we've been looking at systems where we just have really one object, like just a skater, but now we're going to look at two objects colliding with rotational motion involved. Okay, and so we're going to deal with angular momentum with this as well. Since an object that is traveling in a straight line can still set an object or a second object into rotational motion, it can still have angular momentum. Okay, think of this example. If you see a child run toward and jump on a merry-go-round, okay, just picture it running on across the playground, jumping on one of those spinning merry-go-rounds. Even though that child's running in a straight line, when that child collides with landing on that merry-go-round, it's going to set it into rotational motion. That child will act as a point mass about the axis of rotation of the merry-go-round and will apply a torque to that merry-go-round whenever they collide. Okay, so let's take a look at this scenario. So again, same thing. Child runs and jumps on a merry-go-round. Child acts as a point mass with respect to the axis of rotation. So we've looked at our equation for angular momentum, okay, and we're going to deal with the system, the child merry-go-round system. And we know that L, the angular momentum of that system, is equal to I times omega. If I'm looking at just the child to begin with and the child's angular momentum, then the child would be a point mass, and the moment of inertia equation for a point mass is mr squared. And so I could write that the angular momentum of the child initially is mr squared times omega. Again, we got this equation from the inertia notes earlier in the unit. Okay, and I also know that I can get my linear velocity from my angular velocity, or vice versa. Okay, I know that v is r times omega, or that omega is v over r. We've written that both ways, but we can go between the two rotational and translational motions by multiplying or dividing by radius, depending on how we set up that equation. So I can, by substitution, again, omega would be equal to v over r, so I can substitute that in. Because right now, the child is just running in a straight line. I'm not dealing with any angular velocity yet. The child's running at the merry-go-round. Okay, and so if I substitute that in, now I have the linear velocity that the child would have divided by r. And some of those r's are going to cancel because I have r squared over r now. And so that leaves me with this. The angular momentum of that child is mvr, the child's mass times the child's velocity times the radius of the merry-go-round, or the point where the child hit from the axis of rotation. Okay, and that would give us the child's angular momentum whenever they collide. Again, note mv is also equal to momentum, the linear momentum. So you could rewrite the equation like this. Again, depending on what you need and what you have. Okay, you can derive that equation accordingly. But again, this distance r right here is going to be the child's collision point with the merry-go-round as measured from the axis of rotation. So it's the lever arm, okay, but it's the distance from axis of rotation. All right, so when we deal with these linear objects like a child running and colliding with a merry-go-round, these systems will not be isolated, meaning that linear momentum will not be conserved. Okay, because when the child hits the merry-go-round, the child is no longer moving linearly. The child is now on a merry-go-round that is rotating instead. And so he doesn't have linear momentum anymore. He stops moving in that way, and so you don't have conservation of linear momentum. The torque of the two colliding objects, or the torque that they apply to each other, will be internal to the system. Again, if we define our system as the child merry-go-round system, then the torque is internal to that system, meaning it will have no effect on the system's total angular momentum. And so again, depending on how we define our system, if we want to use conservation of angular momentum, we would want to include both the child and the merry-go-round in that system so that we can use that idea of conservation of angular momentum. And we can do that. So let's go ahead and do that now. So example problem, same scenario, child runs and jumps on a merry-go-round. My system is going to be the child merry-go-round system so that there is no net external torque on this system. It is now internal to my system. The axis of rotation will be at the center of mass of the merry-go-round. And so we need to look at the before and after, because again, if we have conservation of momentum, or in this case, conservation of angular momentum, it means that the total initial angular momentum of the system needs to equal the total final angular momentum of the system. And so initially, we have the kid has some initial angular momentum, but the merry-go-round initially was at rest. So a merry-go-round has 0 angular momentum initially. Okay, and then we're going to look at what happens afterward. Okay, I know beforehand about the kid's angular momentum. We derived this equation a minute ago. The mass of the kid times the velocity of the kid times the radius of the merry-go-round. That was one of the steps we did a couple slides ago. That is the initial angular momentum of the kid, plus 0, because the merry-go-round isn't moving initially, would equal the the angular momentum of the kid at the end, which is going to be the kid's moment of inertia multiplied by the angular velocity plus the angular momentum of the merry-go-round, which is the merry-go-round's moment of inertia times its angular velocity. And because they're now stuck together, they will have the same angular velocity because the kid is now on the merry-go-round after they collide. So those values for omega are the same for both, which means we can factor it out, giving us this. Okay, so the moment of inertia of the kid plus the moment of inertia of the merry-go-round, that sum can be multiplied by their shared angular velocity. Now the kid is a point mass. Point masses are mr squared. The merry-go-round is a disk. Again, this would be given to you. I would not expect you to memorize it. Okay, so you would be reminded of the equation for moment of inertia of a disk is 1/2 mr squared. And so I'm substituting in those values for the moments of inertia for each of them. Okay, and so now we have an equation that we could use to solve for any of these variables. I didn't actually give you any numbers. We were just working on deriving something that we could now use to solve something if we had some values. Okay, so again, be able to go through a process like that, those steps of substitution in order to get somewhere where you could plug in. And maybe this is where we need to be and maybe it's not. We could keep going. Again, depends on what we were solving for. But you could use this equation to solve for any of these variables, or you could continue working on that derivation. All right. So again, there is the net internal torque does not cause a change in that system's angular momentum. Again, there was a torque whenever the child hit the merry-go-round and they collided. They applied torques on each other, but because it's internal to the system, we have conservation of angular momentum. But it would cause a change in each object's angular momentum, obviously, because the merry-go-round was at rest. Now it's not. The child was moving linearly. Now he's not. And so you can figure out what the change for each is, again, if you wanted to. Depends on what you're being asked to solve for. All right, so again, you get a change in angular momentum when you have a net external torque act on the system for some period of time. So you do need to watch how you define that system. You could define your change in angular momentum as torque times time. We had, again, a similar equation with linear momentum, with that being change in linear momentum being force times time. So again, it still looks similar to the translational equations you've seen previously. Sorry, that was too fast. All right, I'll give you a second if you want to copy that down. So again, if you do have a net external torque on your system, you can use this equation to figure out what the change in angular momentum is and then work from there, depending on what it is you are solving for. All right, any questions? Not yet. Probably may have some, end up having some as you work through those problems, which is what I'm going to recommend that you do right now because playlist 4 is due tomorrow. So if you would like to, you're welcome to go ahead and get out that you do have a paper task option, workbook practice, or you can work on the worksheet practice or your checkpoint, depending on where you're at. But again, this is due tomorrow, and then as a reminder, you do have a test, 2 tests next week, multiple choice and free response sections. If you guys have questions as you're working, please let me know.